Welcome back to Miss Eddie's Math Movies, where it's cute to be a square. Today's lesson is 5.6, bisectors. By the end of the lesson, you'll be able to use angle bisectors and perpendicular bisectors. In order to talk about these bisectors, we need to define a couple things first. Distance from a point to a line. Well, if I give you a point and a line, and I want you to find how far apart they are, you can't measure like this or like this. So you have to go straight to the line, the shortest distance, which is always going to be perpendicular. So this is the perpendicular length. So when we talk about distance, it's perpendicular. It goes right there. Just like when you get measured, you have to be perpendicular to the floor. You have to stand up perfectly straight. Equidistant, well, you can see the word equal is almost in there. And distance, like distance, I want you to think about this as equal distance. And perpendicular bisector is a line that forms a right angle with a segment at its midpoint. All right, so here's a segment, and then we need a line that makes a right angle. So put in a right angle, and it has to be right in the middle. So it has to be perpendicular, right? That means 90 degrees. And bisect means in half. It has to make a right angle. It has to cut it into two equal pieces. So this right here is the perpendicular bisector. I'm going to highlight that for us. So you got to use both of those words. Okay. Now we're talking about an angle bisector. And we did an activity that kind of had you measure this. If a point is on the bisector of an angle, so here's the bisector, then it is blank from the two sides. Then it is equidistant. So if you're anywhere on this middle line, the distance from here to the side is the same. And notice they had to measure that perpendicularly. It's a 90-degree angle there, and that's really important. Like we talked about up here, when you measure distance, it has to be done perpendicularly. So if 1 is equal to 2, then BC is equal to BD. Where's congruent to? These distances are the same if it's right in the middle. And that should make sense in your head. In the diagram, ray EW bisects TUV. So right off the bat, I know that it cuts this angle into two equal pieces. Then it says UTW is a right angle and UVW is a right angle. I have to prove that this triangle is congruent to this triangle. Well, we've done a lot of this. Let's see what I've got so far. We have an angle that's equal. Oh, and then we have right angles here. And then hopefully you see that they're sharing a side. There's the side that they're sharing. So this looks like angle, angle, side to me. So that's what we're going to use. Now we just need to fill in. Every time we talk about an A, we need to write it in here. Same thing with the S and the A. So this was our given. It wants us to use the angle bisector. Well, because of the angle bisector, we got these two angles. Angle TUW, that's this angle. And the other half was this angle, VUW. Oh, they're using a different, we can use this too. This is fine. How do we know that WT is equal to WV? That's the angle bisector there, what we just talked about. If W is on the bisector, it's equidistant, right? That's what we just talked about. How do we know that these are right angles? Oh, they told us it was right angles. That's given. And how do we know they're congruent to each other? Well, because right angles are equal. Right angles are congruent. And like I said, we use angle, angle, side. Write 3 congruent statements to show the angle, angle, side congruence is used in example 1. All right. So we already did TWU. Let's do TUW. Let's do WUT. And let's do UTW. All right, I need you to match up the letters. So if I go TUW, what do I need to do on this triangle? You're going to fill this in with the appropriate congruence. Go ahead and do that now. Fill in the blank. Now the perpendicular bisector theorem, we did an activity on this too. Here's our perpendicular bisector, and we put a bunch of different points on this perpendicular bisector. And every time we measured, the distances were the same. Once again, we're using that word, equidistant. So if a point is on the bisector, then we know it's equidistant from the endpoints. CA is equal to CB. And we measured those, and we found that that was the same. So using perpendicular bisectors. AC is the perpendicular bisector. There it is. Because AC, so we have to find AB here. Well, we know it's the perpendicular bisector because it's perpendicular and it's cutting in half. And we just learned that if you're on the perpendicular bisector, you're equidistant from the endpoint. So this is the same distance as this. So we know that AD is equal to AB. So that's the equation we're going to write. What is AD? 5x plus 12 equals 8x. All right, now we need to subtract 5x from both sides. We get 3x equals 12. And then divide each side by 3. X equals 4. But notice we're not done. It says find AB. So we need to take this and plug it in right there. 8x, so x is 4, so 8 times 4 is 32. Now the follow-up says check your answer in example 2 by finding AD. So let's also plug in x right there. Now we know these are supposed to be equal, so I hope we get 32. So 5 times 4 is 20, and 20 plus 12 is 32. Awesome. We know we did it right because this was 32 and this was 32. All right, now you have to find the indicated measure. So I want you to write an equation and solve for x. And then you got to plug it back in and find FH. So you're going to plug it in, then you're going to find MK, and then EF. There's 2 separate answers. Go ahead and do this now. Think about what we learned. We've got equidistances here. So set those things equal to each other. If this is the angle bisector and the perpendicular bisector, we know some things are equal that we measured out. In the diagram, MN is the perpendicular bisector. Prove that MST is an isosceles triangle. All right, here's our perpendicular bisector. And we have to show that this triangle has two sides the same. Well, we just learned that if you're on the perpendicular bisector, you're equidistant from the endpoints. So this distance is equal to this distance. So look at, we have an isosceles triangle. That's what the definition of an isosceles triangle is that you have two sides the same. Look, here are two sides the same. That's how I know it's isosceles. All right, last example. A company plans to build a warehouse that is equally close to each of its three stores, A, B, and C. So these are all stores. And we need to build a warehouse somewhere. Well, you want the warehouse to be right in the middle of these 3 points. So first, what we're going to do is we're going to make this into a triangle. So connect A, B, and C. Right, and we want the warehouse to be equidistant. Well, how do we find what's equidistant from endpoints? We do the perpendicular bisector. All right, so we got to find the middle of each side. That looks to be about the middle to me. All right, I'll put check marks there. And then we got to draw a perpendicular line. So that looks like it's making a right angle. Let's find the middle down here. All right, we got to make a right angle. Maybe it should be this way just a little bit more. That looks like a right angle. Now we've got to find the middle over here. All right, 1, 2, 3. And we've got to make a right angle. This is where they all meet. That is what they're calling this point P. Right? Because this is equidistant from all the endpoints. This distance is equal to this distance and this distance. So this is where all the stores should drive to get their products. Because BP is equal to AP and to CP. That's actually, there's a special name for this. This point where all the perpendicular bisectors meet is called the circumcenter. And that's where the stores should put their warehouse. This is M cubed, signing out.